Over the years, electrical safety has been a crucial aspect of working in any industry where electrical systems are used. To effectively practice electrical safety, it's essential to understand some basic electrical concepts: voltage, current, resistance, and power. These concepts form the foundation of how electricity works and why certain safety precautions are necessary. So, what is voltage? Well, it's the force that pushes electrical charges through a conductor, like a wire. Think of it as pressure that moves electricity from one point to another. But why is it important? Well, in simple terms, the higher the voltage, the more potential there is for something to go wrong, like an electrical shock or damage to equipment. Understanding voltage helps you know what kind of protective equipment you might need and what precautions to take. But here is a much bigger concept: resistance. This concept defines a material's opposition to the flow of current. Think of it as the friction that slows down the movement of electricity. In this case, high resistance in a circuit can cause overheating and inefficiencies, while low resistance allows for the easy flow of current. Both extremes can be dangerous if not properly managed. This is why understanding resistance is very important when designing circuits and selecting materials. As for the last concept, power is the rate at which electrical energy is consumed or produced. It's a combination of both voltage and current. Since they're all connected, power tells you how much work an electrical system can do. High power means more energy is being used, which could mean higher risk, such as more heat production. Meanwhile, the current is a much bigger concept used in these kinds of settings. Current is the flow of electrical charge through a conductor. Think of it as the amount of electricity moving through a wire at any given time. Now, unlike the voltage, high current can generate heat, which can lead to burns or fires if not properly managed. It's also the current that's directly responsible for causing electric shock. In essence, even low voltages can be dangerous if the current is high enough. As a matter of fact, knowing the current allows you to select the right type of wiring, circuit breakers, and fuses to prevent overheating and potential hazards. However, this concept is usually split into two categories: alternating current, AC, and direct current, DC. Every type of current has its unique properties and applications that affect how electrical systems are designed, operated, and maintained. The direct current is a type of electrical current that flows in a constant direction. This type of current is found in common batteries, such as those in your remote control or flashlight, and it's also used in most electronic devices like computers, cell phones, and LED lights. On a large scale, DC power supplies are often used in labs for various experiments and equipment that require stable, consistent voltage. On the other hand, an alternating current is an electrical current that periodically reverses direction. The voltage in an AC circuit moves back and forth between positive and negative values. For context, this type of current is used for most of the electricity that comes into your home or workplace. The power grids supply electricity as AC because it's easier to transmit over long distance. Many household appliances and industrial machines like refrigerators and fans use AC motors. This is because it's more efficient for transmitting electricity over long distances, reducing energy losses in power lines. However, a high voltage AC can be very dangerous, resulting in electrical hazards. Now, you may be wondering what specific risks are encountered in the industry. Generally, laboratory workers face 6 main categories of electrical hazards: electric shock, electrocution, burns caused by either electrical or thermal contact, fires, explosions, and indirect injuries such as cuts and lacerations. Electric shock can happen when handling live wires, faulty equipment, or exposed electrical parts. However, electrocution is a more fatal electric shock. It results from exposure to high voltage or current, leading to severe injury or even death. Meanwhile, arc burns result from the intense heat produced by an electrical arc, a high voltage discharge that occurs when current jumps across a gap or from faulty equipment. They usually occur during equipment failures, short circuits, or when working near high voltage sources. Amidst all these electrical hazards, fire outbreaks have always been the most dangerous mishap. Electrical faults usually lead to fires by causing overheating of wires, short circuits, or sparks that ignite flammable materials. Moreover, it's one thing to experience danger from electrical faults, and it's another thing to experience the danger of static electricity. This type of electricity is formed from the buildup of electrical charge on the surface of objects. They can discharge flammable vapors, gases, or dusts, leading to fires or explosions. Additionally, they can damage sensitive electronic components or disrupt their operation. While all these electrical hazards may sound scary, there is a way to avoid being a victim of such unfortunate events. Take, for example, faulty wiring and connections. Lab workers can always look for frayed wires, exposed conductors, or loose connections. In response, you can replace any damaged or worn out wires immediately. As for overloaded circuits and improper use of extension cords, ensure extension cords are rated for the power they carry and are not damaged. You can always use extension cords only as a temporary solution and ensure they're rated for the intended load. While providing solutions to overloaded circuits, you can also ensure all wires and cables are properly insulated and protected to avoid problems of inadequate insulation. Overall, ensure that all equipment with 3-prong plugs is properly grounded and connected to a suitable ground. This solves the problem of defective and ungrounded equipment.